So there's two main classes of mechanisms for redox reactions in transition metal complexes. The first is called the Intersphere electron transfer. In this mechanism, you have electron transfer that's mediated by an intermediate with a bridging ligand. Okay? And then you also have what's called outer sphere electron transfer. This is more quote unquote direct. We'll see what that means in a future video, one where we really dive deep into details of outer sphere electron transfer. But you don't have this bridging ligand that facilitates the electron transfer. So we're going to start with inner sphere electron transfer. And I think you'll see what I mean by how this bridging ligand works. So consider this reaction that I showed you previously in the previous video, where you had a cobalt chloride with amine ligands also in it, reacting with a chromium complex, okay? And so first, what I want to just go through is a little bit of, what the lability of these are. And in order to figure out the lability of these, we want to look at the electron counts, okay? And so if we do this, right, remember that this was a cobalt 3+, and so if it's cobalt 3+, cobalt 3+, that is going to have how many d electrons? Well, neutral cobalt has 9 valence electrons, so cobalt 3+ is going to have 3 less than that, so it's going to have 6 valence electrons. This is high spin, okay? And so you can look at the spectrochemical series, and this is a borderline case, but you can measure this and figure out that it's high spin. This is a D4 complex, chromium, right? If we look at our periodic table, chromium is in the 6th column. So if we have a 2+ chromium, that is going to be D4. And cobalt in the 2+ is going to be D7, and chromium in the 2+ is going to be D3. All right, and so we can think about the lability of these. Most of these are going to be pretty labeled. If we look at the lability rules in the previous video that we talked about. But the D3 is definitely going to be very inert. D3 has a lot of crystal field stabilization energy, and so it's very inert. And so this is partially what drives this reaction. That's why I bring it up. You make a very stable product. You start with two things that are pretty labeled, and if you make one inert thing like that, well, that can a lot of times drive the reaction forward, because you've made something that's very thermodynamically stable. All right, so the mechanism for how this happens. First, you're going to form a bridged intermediate. And so what's that going to look like? Well, you take the two precursors, the cobalt 3 precursor and the chromium 2 precursors, the two reagents, the two reactants, and then you're going to form a bridged intermediate. You need a ligand in there that can form a bridge. Halides can. They have multiple lone pairs, so they can form bridges, okay? Mu chloride complexes, going back to our coordination chemistry nomenclature, are very well known. Mu chloride complexes, mu, remember, represents a bridging ligand. And then you're going to do electron transfer via that bridging ligand. So what's that going to look like? It can happen in a few different ways. Here's a very common way. You have one electron go to the chlorine, and then that electron's going to go to the other metal center, okay? And so for a second there, or a nanosecond, right, you're going to have an expanded octet on chlorine. You're going to have one extra electron, depending upon the order of all this stuff that happens. And that gets really details that's hard to figure out. People do care about it. It's hard to figure out. But anyway, you can see how, because chlorine can have an expanded octet, it could facilitate this sort of hopping of an electron, so to speak, okay? So once you get that, now you have your metals, your cobalt and chromium, in the same oxidation state that they are in the products, okay? Cobalt's in the second oxidation state, chromium's in the third oxidation state. At this point, you can do the last step, which is the dissociation of the bridge complex. So the bridge complex is going to fall apart, and then you're going to get your final complexes, okay? So electron transfer through the bridge, that's really the key step, and it's kind of neat. How do we know that this happens? How do you know if you have a mechanism that is occurring through an intersphere process? The way that you know, the best way that you can know is by doing an isotopic labeling experiment. So for example, if you do an experiment and you put chlorine, free chloride, in the solution, so you put some sodium chloride, but it's specially isotopically labeled with chlorine 36. The main isotopes of chlorine are 35 and and 37, I believe. So if you use 36 and it's enriched in 36, what that can tell you is if you do this and you put this isotopically labeled chloride in free solution, none of this chlorine 36 will be detected in the product, okay? And you can figure that out using mass spectrometry. You can do the opposite. You can isotopically label your starting material, okay? And then show that all of the product includes the chlorine that's isotopically labeled. Either way will work, but this is evidence that you're not getting chloride from somewhere else. And the chloride's not exchanging with solution. So that means it must be a bridge. There's no other mechanism that's consistent with that experimental observation. So like I said, you need a ligand where you have usually multiple lone pairs that you can have this bridging set up. So these are things like the halogens, azide, thiocyanate, and cyanide also can bridge. Usually in these cases, electron transfer is the RDS. But if both products are inert, dissociation of the bridge complex will be the RDS. And so think about why, okay? Let's say you have this reaction. This reaction, you have inert and a labile complex reacting to give two inert complexes. Well, if you have two inert complexes, now you have this bridge intermediate and they're both inert. And so it's actually going to be, they're pretty stable like that. That bridge intermediate is pretty stable. You're going to be able probably to isolate that bridged intermediate, right? If you wanted to, which is further evidence that this intersphere electron transfer mechanism is occurring in this case. But that's going to be the rate determinant step. It's always nice to kind of look a little bit into the history of chemistry, very fascinating. And maybe I'll make some supplemental videos for you guys about some of my favorite things, components of the history of chemistry. Henry Taube won the Nobel Prize for his work just on intersphere mechanisms and electron transfer. It was great work. He did those isotope labeling experiments that I talked to you about and figured out this mechanism. And so, yeah, he worked at Stanford when he did this. So, with intersphere electron transfer, here you have, in this case, there's some intricacies that can happen here. Here in this case, you have two very different rates, right, that are changing by a factor of 10 to the fourth. And this is an interesting case where you have two metals that are attached by a ligand, by a bidentate ligand, right? And what's interesting here is that in this case, you have sort of the para-substitution, right? So this is a carboxylate derivatized pyridine ligand. But here is the carboxylate is in the para position to the nitrogen on the pyridine. And here the carboxylate is in the meta position, okay? And you can see the meta position for, in this case, this complex, the electron transfer between the cobalt and the ruthenium occurs much, much slower than in the para position. And so this is good evidence that intersphere electron transfer is happening in this case. And why is that? Because all the ligands are the same, but now you kind of affected the sterics of things by changing the position in which they're arranged. And so apparently, what's apparent from this is that since this has a slower rate, it must be a lot harder sterically to make a bridging species where you have bridging occurring, and then electron transfer can occur. All right. So versus this para situation. So that's just an interesting case where you have these sort of interesting dimers, okay, and electron transfer occurring.